Hello there. Welcome to my talk, Structured Learning of Cyclic Linear Causal Models, in the session of Network Analysis and Causal Modeling. My name is Carlos Amendola, and I will tell you about joint work done at the Chair of Mathematical Statistics of the Technical University of Munich. Our research group is led by Matthias Durton, who supervises PhD students Philip Detling and Jun Wu. We collaborated with visiting PhD student Federica Honori from Rome. A linear causal model consists of a random vector x which solves a recursive linear equation with error epsilon. Epsilon has covariance matrix omega, not necessarily diagonal, which means the errors can be correlated. Then x is given by the inverse transpose of the identity minus lambda times epsilon, and has covariance matrix as displayed. We're specifically interested in models restricting the support of lambda and omega, encoded in a mixed graph. Indeed, we define a linear Gaussian model given by a mixed graph as a set of parametrized covariance matrices so that lambda has support determined by the directed edge set V, and omega has support given by the bidirected edge set B. Okay, here is an example. Here we have a linear Gaussian model with 4 variables related by the linear equations on the top left. These are conveniently represented by the mixed graph on the right. Here, the blue edge weights are the coefficients in the linear equations, while in red, we mark the bidirected edge weights and the node variances. So the bidirected edge weight omega 1,4 means that there exists a latent variable that has influence on both x1 and x4. Here we also show the 2 sparse matrices lambda and omega explicitly. In this example, the graph is simple. This means there is at most one edge between any pair of nodes. We will focus on this kind of graphs. These are our main theorems. The expected dimension theorem says the linear Gaussian model given by a simple mixed graph has dimension equal to the parameter count. Note that in particular this means that if 2 graphs induce the same linear Gaussian model, in which case we call them distributional equivalent, they must have the same total edge count. In other words, the expected dimension theorem provides a necessary condition for distributional equivalence. Namely, 2 equivalent graphs must have the same number of edges. One note of caution: this result is not true anymore if we drop the hypothesis that the graph be simple. The skeleton of a graph is the underlying undirected graph obtained by removing all directions from the edges. A collider triple is obtained when 2 arrowheads meet at a node. The sufficient condition theorem states that 2 graphs with the same skeleton and collider triples are distributional equivalent up to closure. So this implies the linear Gaussian models are equal up to a measure 0 set. This theorem generalizes the sufficient condition for distributional equivalence found by Nausauer, Matthews, Evans, and Bullman for both 3 acyclic path diagrams. That is, they prove that 2 simple acyclic mixed graphs having same skeleton and collider triples must be distributional equivalent. I also want to mention that while our result involves equality up to closure, currently we do not know any examples where the models are not exactly equal. I will not get into any technical details, but I will just say that allowing for cycles introduces subtle difficulties for both theorems, and our proof techniques have a certain algebraic flavor. To perform model selection, we propose a score based on the log likelihood and a BIC type penalty. We consider standard BIC and an extended BIC. The latter has an extra term and tends to find sparser graphs. Since the model space is huge, we use greedy search. It starts at some initial random graph generated by Markov chain Monte Carlo simulation. Then, at each step, it traverses the local neighborhood of the current graph by adding, removing, or changing one edge. Finally, the search stops when no higher score in the local neighborhood is found, or when the maximum number of iterations is reached. To address the issue of local optima, we restart the greedy search hundreds of times. Okay, so this table shows results for 5 variables, 100 simulations, and 300 restarts for each. By our theorems, the proportion of models with same dimension as the true one gives an upper bound on the proportion of recovered graphs that are distributional equivalent to the true graph. Likewise, the proportion of obtained graphs with same skeleton and collided triples is a lower bound. We use different sample sizes. For n equals 10,000 samples, the true proportion of obtained distributional equivalent graphs to the true one ranges from around 0.4 to around 0.7, as highlighted. The structural Hamming distance, SHD, is the number of edge changes, that is, additions, deletions, reversals, needed to take one graph to another. Here, SHD star is the minimum of all SHDs among all pairs of graphs that can be certified equivalent by our theorems. In the highlighted lines, it's about 2. That means, on average, our estimated graph needs 2 edge operations to reach the true equivalence class. We also apply our method to protein expression data from Sachs et al. It consists of 14 datasets of 11 proteins in human T cells, obtained from different experimental conditions. Cycles are expected because of self-regulation of those proteins. Here, we adopt a Gaussian copula model, which assumes every variable is a transformation of some latent Gaussian distribution. Then, we use Kendall's tau correlation matrix as the covariance input and choose extended BIC. Here are 2 estimated graphs using our method. Note the second graph presents a directed 3 cycle. Our estimation results are in agreement with the Sachs et al. Paper, and we find some novelties as well. For more details, we invite you to read our paper, which was presented in the Conference on Uncertainty in Artificial Intelligence, UAI, this year. I list here a couple of references, and I thank you for watching.